Now we ask what happens in the same system if the initial velocity is 3 meters per second instead of 0. Well, nothing that we did in calculating the net force has any effect, is affected by the initial velocity. The net force is still the force of gravity on the 3 kilograms, the 29.4 newtons. The mass of the system isn't affected by the initial velocity, so when we divide the force by the mass, we're still going to get 1.96 meters per second squared. The acceleration of that 3 kilogram mass is still the same, and that's all we needed to find the string tension, so that's not going to change. And the work done on the system is still 85 joules, because we still move the same distance under the same force. The change in potential energy is still negative 85 joules. The change in kinetic energy is still plus 85 joules, for the same reason the work in the system is still 85 joules. The thing that changes, however, is the final velocity and the final kinetic energy. The things that change are the final velocity and the final kinetic energy. The final velocity is calculated the same way as before, but this time the initial velocity is 3 meters per second, and when we factor that into the equation and use the acceleration in delta S from before, we come up with a final velocity of 4.51 meters per second instead of the 3-point-some meters per second we had earlier. And that stands only to reason. Since we have an initial velocity that's greater than before, our final velocity is going to be greater than before. Final kinetic energy, well, we could just do 1/2 mv squared on the 4.51 meters per second and we'd get 153 joules, but it's more instructive to say, okay, the final kinetic energy is the initial plus the change in kinetic energy. The initial kinetic energy is 1/2 the mass times the initial velocity squared. The change in kinetic energy from before is still plus 85 joules. The initial kinetic energy, the kinetic energy we have by virtue of starting out at 3 meters per second, is 67.5 joules. We add that to the same change in kinetic energy, and we again get 153 joules. Another variation on the problem is to assume a frictional force. Now this small mu, this Greek letter mu, let me write. Okay, it looks just like that. This one could be improved upon a little bit. Okay, is 0.06. Well, the meaning of mu is simply when you have two objects pressed together by some force, then the friction between those objects when they try to slide across each other will be this proportion of that pressing together force. Now that applies to the 12 kilogram object sitting on the tabletop. I haven't drawn the tabletop here, but gravity's pulling down with 117 newtons of force on that object, so that the weight of the object is 117 newtons. We get that, of course, by multiplying the 12 kilograms by the 9.8 meter per second squared acceleration of gravity. So we see that the object on the table and the tabletop itself are being pressed together, if you will, with a force of 117 newtons by gravity. So that the frictional force as this object slides across the tabletop has to be 0.06 of that pressing together force. And that turns out to be very close to 7 newtons. So we have a frictional force of about 7 newtons. Now, with a frictional force of 7 newtons tending to retard the system's motion, the system, of course, trying to move in this direction with a 29.4 newton force, we get a smaller net force than before. The friction decreases the net force that we would otherwise have if there was no friction. So the net force is 29.4 newtons minus 7 newtons, and we're just going to say it's about 22 newtons. Of course, you can calculate it to as much precision as you wish. So the acceleration of the system, which has now a net force of only 22 newtons, decreases. Before it was close to 2 meters per second. Now we calculate it by dividing the force by the mass, and we get about 1.49 meters per second, giving us a final velocity V naught squared plus 2A delta S. Now, I'm assuming here that we're back to the original statement where V naught was 0. If we use this acceleration and the same delta S, the 2.9 meters, we get about 2.94 meters per second. The work done by the net force is 22 newtons times 2.9 meters, or only 65 joules. Before, when the net force was higher, the work was the work done by gravity, which was 85 joules. Now we can put all that together as follows. The final kinetic energy is 65 joules, which is the change in kinetic energy, which is also the work done by the net force. Has to be. Change in kinetic energy is the work done by the net force. The change in potential energy, gravitational potential energy, is negative 85 joules because, again, gravity did 85 joules of work on the system. And the work done by friction is 7 newtons times the distance moved, or 20 joules, or the work done against friction. This is the way we want to think about it. This is the work done by the system against friction. In order to move forward, the system has to exert a 7 Newton force against friction for the distance of 2.9 meters, therefore does 20 joules of work. That's the work by the system against friction. Now, the work done by the system against friction plus the change in the potential energy plus the change in kinetic energy is what? Well, we add these up and it comes out 0 again. This is going to be a general principle. This is getting toward a statement of energy conservation. Remember, before, when we had no friction, the change in potential plus the change in kinetic was 0. The potential decreased, the kinetic increased. Now there's work being done by the system against friction, and the total work done by friction and the change in kinetic energy is now what has to equal the opposite of the change in potential energy. So that the work that we could ordinarily get from the system, if there was no friction, gets split between kinetic energy gain and work against friction. So, alternatively, we can see that gravity does 85 joules of work, which would, in the absence of friction, then tend to increase the kinetic energy of the system by 85 joules, that friction does negative 20 joules of work on the system. Therefore, the net work done on the system is 65 joules plus 65 joules, so the kinetic energy change is 65 joules. Now, all this, where the energy is supposed to be plus and where it's supposed to be minus, is rather confusing now, but we're going to go on to clarify that before long.